darlings and explorers of the unknown. Welcome to Ask an Astrobiologist, the show that celebrates the science as well as the scientists involved in our quest to understand the nature of life. I'm your host, Dr. Graham Lau, also known as the Cosmobiologist, and we're brought to you by the NASA Astrobiology program and SaganNet.org. As always, we want to thank all of you who watch our show, who tune in from month to month to share in the celebration of astrobiology and planetary science, space exploration, the missions of NASA, and so much more. This month, we want to highlight one of our past guests actually shared about today's episode. So a very huge thank you to Morgan Cable on Twitter at @StarsAreCalling for sharing about this episode. You might recall that Morgan was our guest on episode 16 of the show, and we talked about worlds like Enceladus and Europa and Titan. And so that's especially fitting for today's show, which is going to be most excellent. I'm super excited. Tomorrow is the 368th anniversary of the discovery of the moon Titan, the largest moon of Saturn, and indeed the second largest moon of our solar system. It is a world that is obscured by a thick, hazy atmosphere rich in hydrocarbons and organic molecules. And as we'll discuss in today's show, there is an upcoming mission being developed by NASA and through the Johns Hopkins University Applied Physics Laboratory called Dragonfly that's going to allow us to better explore the geology, the chemistry, the atmosphere, the world of Titan. And so that's super exciting. I'm so glad to have today the principal investigator, the lead on the team for Dragonfly joining us. Dr. Zibi Turtle is here. Dr. Turtle earned her BS in physics at MIT before going on to earn a PhD in planetary science at the University of Arizona. She spent some time as a postdoc at U of A, as well as with the Planetary Science Institute, before then joining APL in 2006. She's been involved in a number of missions like Galileo and Cassini, the Lunar Reconnaissance Orbiter, the upcoming Europa Clipper, and like I said, now Dragonfly. And so thank you so much for joining us for Ask an Astrobiologist, Dr. Turtle. It's a pleasure to have you here.
Thank you. I'm so happy to be here talking with you today.
This is super exciting. So tomorrow is the 368th anniversary of the discovery of Titan. We've had a few spacecraft fly by Titan and one visited in the past, but of course this is going to be a really cool mission with Dragonfly and with you as the lead. Before we jump into my questions, though, about Dragonfly and Titan and all of those cool things, one thing we love to do on this show is celebrate the scientists and the career pathways that we follow to develop these careers in planetary science and astrobiology. And so I'm wondering for our audience, could you share with us kind of what was the beginning for you, your science origin story that really got you into this realm of planetary science?
Yeah, absolutely. I have always been interested in astronomy since I can remember. I don't actually remember learning the names of the planets. They've always been kind of part of the geography. My grandmother knew all the mythology of the constellations. My father had majored in astronomy. He worked for the Air Force studying atmospheric phenomena here on Earth, and so we were always looking up as kids. My sister and I even had a game called Space Hop, where you got to you would get different missions. And so it had the board was a map of the solar system, and the missions would be, go to the planet that has this, or go to, the world that has this. And one of the fascinating things that we got to see as we played that game growing up was that at the same time, the Voyager spacecraft were moving out through the solar system. And so we learned, the answers to the questions so that we could do our missions in the game. And then we learned what was updated as Voyager discovered that Jupiter had more than 12 moons and things like that. And so it was not only a fun game that we played all the time, but it was also just so exciting to see how much we still had to learn about the solar system and how to get to watch that and see it happening in real time. So that's what kind of grabbed me into that this field.
I love that so much. And honestly, I almost steer clear of ever mentioning how many moons Saturn and Jupiter have anymore because we keep finding new ones. Exactly. And also, I was just speaking to some school students in California the other day, And I mentioned how like they have Star Wars Legos now. And when I was a kid, I had to use a model rocket engine igniter and melt the Lego plastic myself to make my Star Wars Legos. Are there things that the kids these days have to learn about planetary science that kind of makes you maybe a little jealous or maybe inspired to know that they have a brighter future here?
I'm certainly jealous of all the Legos. In fact, I still build Lego models. I did that a lot as a kid as well, and all the different kinds of blocks you have these days compared to a few decades ago is there's certainly a lot more there that's really fun to play with, which I enjoy. I mean, we know a lot more. There's just so much we've discovered about our own solar system and solar systems now beyond ours in the last few decades. But a lot of times what that tells us is how much more we have to learn. And so they're just more stepping stones now, I think, especially as we learn about more and more extrasolar solar systems, which is just thrilling.
Yeah, absolutely. I mean, over 5,000 exoplanets now are known to exist. It's mind-boggling. And that's a good transition to talk a bit about planetary science. When in your career, so you went to MIT and then went on for a PhD in planetary science, but when did you realize that, you really wanted to pursue a career in research in planetary science?
So when I started in college, I knew I was interested in astronomy. I chose to major in physics because it was broad, because I knew with a physics degree I could go in a number of different directions. And in fact, initially I took a bunch of astrophysics courses, which is fascinating, right? Cosmology is spectacular and mind-bending. But as I took more courses going through my undergraduate degree, I started taking more planetary planetary science classes. And the accessibility of the solar system was kind of what brought me back into the solar system from the broader the broader field of astronomy. In particular, the kind of, again, still watching the Voyagers go out through the solar system was very inspirational, and so that's kind of what prompted me to continue study in planetary science specifically. But again, I actually I went to a graduate program that was very broad. Because I wasn't sure which area of planetary science. It's such a broad field. It's basically all of the fields that we have here on Earth, but then applied to, the solar system together. So, so I went to a broad program so that I would have, still some opportunity to explore different areas and see what I wanted to study as, moving forward in my career.
That's fantastic. Yeah, and I think for our audience, who are interested in astrobiology, they likely know that, in the realms of planetary science and astrobiology, geobiology, these kind of larger, diverse realms of study, they really do include so many different pursuits from different sciences, different realms of engineering. Now, in your career, like I mentioned earlier, you've been involved with Galileo and Cassini, LRO, and now the upcoming Europa Clipper. What was the pathway for you to get involved in mission science and then to kind of take on leadership roles in mission science as well?
As a graduate student, for my dissertation, I was studying impact cratering, the impact cratering process, and I was using numerical models to simulate impact craters the formation of impact craters on other planets to understand what we can learn about the planet itself, what the final morphology of an impact crater can tell us about the planet itself. And another graduate student, a colleague of mine at the University of Arizona, Cynthia Phillips, and I she was working with the Galileo mission, and she was studying images of the surface of Europa. And Europa, of course, is a fascinating target from a perspective of impact cratering because the ice shell on Europa may be relatively thin. And so we started collaborating on on modeling cratering into ice shells, and using the data that Galileo was sending back at the time, and another colleague, Betty Pierazzo, and I modeled different aspects of the impact cratering. So so there was a kind of a project there, and then that kind of started that connection to the mission that was sending the data back. And after I finished my graduate degree, I had a postdoctoral position supporting the Galileo program, but planning the observations for Io, which is another totally fascinating moon we could talk about. But that was the first mission role I had, was planning the imaging observations with Galileo of the moon Io. And from that, the next step in my career was, after the end of the Galileo mission, I started working with the Cassini mission. Again, working with the imaging team, planning the observations of Titan. And so that was my first, my first connection to Titan, and exploring that. Which was spectacular, right? We went from, and we did this so quickly, right? Just 2 decades ago, we didn't know what was on the surface of Titan. We were, just getting ready for Cassini to arrive in 2004, and we had this incredible whirlwind of going from knowing very little about the nature of the geography and the geology of Titan to mapping it and understanding how Titan works as a system in just several years. So that was spectacular to get to participate in, and of course an exceedingly valuable experience in terms of future, planning future missions.
Oh, that's fantastic. Yeah. A great time just to drop in a quick poll for our audience as well on YouTube, since you just mentioned Cassini arriving in the Saturnian system. We had, of course, the Huygens lander, which went down through the atmosphere of Titan, and it really was an atmospheric probe, not really intended to be a lander, but it did land, and we have an image from it. And it did a lot of research. And so we have a question for our audience. With Dragonfly, we're looking at spending at least 2 years, if not more, on Titan. And so our question for the audience is, how long did the Huygens probe survive on the surface of Titan? And we have a few answers popping up right now in the chat. 1 year, 6 months, 2 weeks, 4 hours. Tell us what you think, and I'll come back to that in a little bit. Of course, in talking about the Huygens probe and Cassini and talking about Dragonfly, we did have Melissa Trainer on the show back in 2020, in November of 2020, for our 37th episode. And so much has changed since then, bringing us up now to having Dr. Turtle on to talk about where Dragonfly is now. So it's so cool to hear this connection of Galileo and Cassini. Of course, you worked on LRO and Europa Clipper now as well, which is also another incredible mission coming up very soon. But I think for time's sake and for our audience, I know they want to hear about Dragonfly. I wonder if you can speak to us now a little bit about the mission of Dragonfly, what we will be observing with Dragonfly, and how much knowledge it could bring to us.
Oh, absolutely. So after the Cassini mission, right, we spent 13 years in the Saturnian system, with 126 flybys of Titan. We know a lot about Titan. But one of the big outstanding questions is what the solid surface materials are made of. And when NASA added Titan to the New Frontiers mission target list in 2016, as an ocean worlds target in the New Frontiers program, we started brainstorming about how we could best find answers to the question of what these materials are. And the reason this is important is that Titan is a very special target from an astrobiological perspective. Titan's atmosphere, which is unique among moons in the solar system. In fact, its atmosphere is denser than Earth's atmosphere. The second most common constituent in the atmosphere after nitrogen at Titan is methane. And the methane breaks down at the top of the atmosphere, and the molecules recombine to form very, very complex carbon-rich molecules. These are what form the haze in Titan's atmosphere, but they ultimately fall out onto the surface. And Titan being an icy satellite, when that surface melts at the site of an impact crater, say, or if there is cryovolcanism on the surface, now you have all of the ingredients we know to be necessary for life in terms of there's abundant carbon-rich material that's all over the surface, liquid water at the surface in the past, as well as in the present day in the deep interior ocean inside of Titan, and energy. And so what we want to do with Dragonfly is go to Titan's surface and see and pick up the results basically of these chemistry experiments that Titan has been running for us, these prebiotic chemistry experiments. If you put all of this together, for some period of time, how far does the chemistry, the chemistry progress, the organic synthesis? And because we know what Titan's surface is like, we know there are a number of different places that we'd like to go to make these measurements of the different geologic environments with different geologic histories. And the atmosphere, again, gives us this opportunity to travel on Titan by flying instead of driving. And so Dragonfly came out of this thought process and is an octocopter, a rotorcraft lander, that is designed to, like the rovers on Mars, take everything with us from place to place, and to make measurements of the chemistry and observe aspects of the Titan environment in a variety of places on the surface.
That's so awesome. Just looking at the pictures of Dragonfly, it looks like it's going to be a very cool spacecraft. It must be so cool to be involved in that process too of development and design. I've read that it's going to land somewhere in the Shangri-La dune fields, and the primary mission phase is maybe 100 miles worth of flight, maybe 20 different landing sites. How much went into landing site selection? Are we sure of even the pathway that we're going to follow yet, or will that kind of like come, as we're exploring?
We know the targeted landing area. So the Titan environment is surprisingly Earth-like in terms of its geology, right? It's an icy satellite in the outer solar system with a surface temperature of 94 Kelvin. And yet the features we see on the surface are very familiar. And Titan's equatorial region is covered in these spectacular organic sand dunes. We don't know how you form organic sand, but Titan does, and it's there waiting for us. And so we want to land in and among the sand dunes for a couple of reasons. One is that the sand is organic in composition, and it's very widely sourced. And so this will give us information about materials across the surface of Titan. Kind of like the Mars Pathfinder landing site was chosen to be a place where a lot of different materials came together in at the base of a outflow channel. So you had opportunities to make measurements of materials that came from much further away than you can travel. The other reason the dunes are great is that these are a very specific kind of dune, these longitudinal dunes. And so they have very broad, flat interdune areas between them. Compositionally, these areas have water ice as a component, and so they will be able to tell us about the kind of primordial crust of Titan in terms of its composition, but they're also big, broad, flat areas, and so that's perfect for initial landing sites. And so that's why we're landing in the sand dunes, because we've characterized these areas well with Cassini, and we can design a lander to land in these areas. And then the landing site is close to the Selk impact crater, which is an 80-kilometer diameter impact crater. And so that gives us, by traveling through the dunes and interdunes and then into the deposits associated with the impact crater itself, we'll be able to make measurements of the composition of the chemistry in these environments where impact melt, liquid water, and complex carbon molecules will have had the opportunity to mix.
Well, that's very cool. And also, so there is some potential that there is an ocean under Titan's surface based on Cassini measurements. Do you think that impactor might have even interacted with the subsurface ocean and potentially done some mixing as well from that material? Is that possible?
So the ice crust on Titan is very thick, probably at least 100 kilometers thick, if not thicker. So this impact crater may not have, been able to affect that entire ice shell. Although there is always fracturing beneath impact cratering, and we don't know the structure of ice shells in general in detail on these satellites. So we don't necessarily expect that this crater would have had a direct connection to the deep interior ocean. But one of the things we want to understand is what the opportunities are for exchange through the ice shell. So in addition to taking images to understand the details of the geology and what that can tell us, whether we see evidence of fractures, for example, at the surface, one of the other things Dragonfly will carry is a seismometer, and this will allow us to listen for Titan quakes, to understand how seismically active this icy ocean world is, and that will help us constrain the possibility for exchange between the surface and the deep interior liquid water ocean.
Yeah, that's fantastic. I do want to come back for our audience real quick to that poll we asked earlier for how long Huygens survived on the surface. We offered you options of 1 year, 6 months, 2 weeks, or 4 hours, and roughly 60%, almost 60% of the respondents got that correct, around 4 hours. That's including going down through the atmosphere and then the actual arrival at the surface. There was a lot we didn't know with Huygens when it got there. Did we think there was any potential of Huygens just sinking into one of those ethane lakes, or just sinking into the surface? Because we really didn't know what the organic surface would be like at that point, right?
We didn't know what the surface was going to be like, and we did know that there was likely to be liquid in the system. In fact, Titan has a methane cycle like our water cycle, right? It's rainy here today, right? Titan has methane, clouds and rain and lakes and rivers and seas. And we didn't know how much of the surface would be covered in liquid and where that liquid might be. So Huygens, the probe, was actually, this is spectacular. Huygens was designed to be able to make measurements of a solid surface if it landed on a solid surface, and to be able to float if it landed in a liquid on the surface of Titan, and to make measurements of that liquid, which is a great feat of engineering, to be able to design a probe to land in two such different environments and make measurements. And of course, it landed on a solid surface and sent us back images as well as data about that surface.
Absolutely. And there's that one famous image I think that I've shared in so many of my own talks when speaking about Titan itself, where we see just like this surface with a haze above and then these boulders of ice covered in organic goop. It's so incredible. I'm so excited for Dragonfly. And also, we just today, before our show, we can now talk about this. Dragonfly just passed a very momentous period in mission design, development, and planning called the preliminary design review. I wonder if you could just speak to that process, especially for those who maybe are more science-focused and don't really understand how mission development and the engineering side of things goes.
Yeah, so Dragonfly was selected in 2019. That was selection by NASA to be the next mission in the New Frontiers program. And at that point, we started our preliminary design phase. So there's a series of phases one goes through in terms of the mission development. And so this phase, we spend more time looking at the aspects of the design, really refining that design, doing some of our testing of some of the hardware that's going to need to survive in the Titan environment, for example. And so it's been a very busy period of time, and that culminates in a series of reviews of preliminary design reviews of our subsystems and our instruments. And we had all of those last year. There were more than 20 individual reviews through last summer and fall. And then we had a full-up mission review. This is a week-long review with an independent standing review board who come here to APL, and we spent a week talking about all things Dragonfly and presenting the current design, getting feedback from them that then we carry forward as we move into the next phase. And so that's what that's the milestone of that preliminary design review, or PDR, and the team did a spectacular job. And everyone's really, the review board was very, gave us great feedback, and we passed our preliminary design review and are now looking ahead toward the next steps.
Fantastic. I do briefly want to mention another poll that we had online on Twitter through at NASA Astrobio, which is the NASA Astrobiology program's Twitter account. We asked everyone who was tuning in during Dragonfly's primary mission of roughly 2 years exploring the surface and clouds of Titan, what aspects of the moon most excited them or they could learn about. And over half of respondents said surface sampling, but a large number also said aerial imagery and atmospheric measurements. And we had a much smaller number who are interested in seismic studies. That's kind of sad for me, since I also love geophysics and geochemistry, and understanding the interior of a word I think is super important. But it was very interesting to see that from our audience as well. So thank you for everyone out there who voted in that poll and who, again, tunes in for our show. Dr. Turtle, I do want to just change now just a little bit. I do want to jump to our audience questions as soon as I can. So I do want to hear a little bit from you, if you wouldn't mind, for our audience, speaking to the value of mentorship in your own career, as well as this process of now kind of becoming a leader of such a large team, developing a mission that it'll take time to develop and launch and land and then do the science. I mean, these are long-term, parts of your career that you're now leading. So I wonder if you could speak to, especially our younger audience members who might want to follow in a similar pathway.
Yes, and especially in terms of outer planet exploration, right? These are long-term processes, long-term projects, and they give us the opportunity, and I feel the responsibility to really work with generations of scientists and engineers as we go through the process. And one of the things with Dragonfly that we're able to do is bridge from the generation of scientists that designed and built and operated the Cassini and Huygens mission to the current generation, and then forward to the next generation. Dragonfly is scheduled to arrive at Titan by 2034. And so we will, be working with students and early career scientists along the way, and that's something that we have built into our program to be able to provide mentorship, to provide experience, to broaden participation in missions, and find ways to give people opportunities to learn about missions. Even now in the mission development phase, we're not getting data from Titan, but there's so much to learn about how, what's needed to put to design and eventually, integrate and test to the hardware before we launch Dragonfly to Titan. And what we want to be able to do is bring people in at each step of the way to give experience to the next generation of planetary explorers.
I love that. And so those watching right now, maybe in the future, you'll be part of the Dragonfly mission. We've had past viewers of previous episodes reach out and find possible PhD mentors and guides and advisors along the way in their own careers through our show. So keep an eye out. Another place, Dr. Turtle, where you kind of been in this role of teamwork and being part of a team is in your own kind of realm of rowing, of doing crew rowing. And we always love hearing the human stories about the scientists who join us. And so I'd love to hear about your rowing experience and how that's been part of your life, as well as you're also a taiko drummer. So I'd love to hear about these things and how they help make you kind of round out your life.
Absolutely, yeah. I was fortunate enough to be able to learn taiko when I was in Arizona, in Tucson, Arizona, with a group there, Udaiko Sonora, and it was a lot of fun. And a very different dimension, right? To getting to play drums, to perform. It was just such a different dimension from doing computer modeling during the day. And it's always nice to have these other kinds of outlets. And when I moved, I actually rowed for a little bit in college. And when I moved back from Arizona, there's not a lot of rowing in Tucson, Arizona, given the climate there. But moving back here to the East Coast, I joined the rowing club up in Baltimore. And I've been rowing together with a team there and competing for quite a while now, and it's really excellent to again, to kind of balance things, out, right? If I'm out in the boat, you can't really be thinking about work, or something's going to go wrong in the boat. And so it's been a great balance in that sense. And also in terms of the teamwork, I love working together with teams. So, rowing in a boat together with a team where you all have to be in sync, and, everyone kind of playing their own role, right? And that's the same thing we do on planetary missions. These are very large and very broad teams with wide arrays of expertise. I really love that in whether it's for play or for work.
That's awesome. And it's always fun to hear about those things that we all have in our lives that kind of bring us down to earth and give us a chance to be part of teams, whatever that looks like, and have these other interests. All of us who've studied science and pursued careers in science and engineering have things that make us very human. I do really want to get to our audience questions. I see a lot of them flowing in already from our YouTube audience and from Twitter. Before that, though, we have our Faster Than Light segment, some fun rapid fire questions, just to hear a bit more about your interest in astrobiology, but as well as other things that have interested you in your career. So first off, what is your favorite answer to Fermi's question, where are they?
So I think it's an intriguing question, from the perspective of trying to understand our place in the universe and where we fit in. I think that there are a lot of aspects. I think it's telling us there are a lot of things we don't know yet. And so a lot of the answers get at, what aspects of the universe, of the development of life, et cetera, don't we know? And I think it really helps us to kind of compile that, a set of things we still need to learn about, and use as a guide to look for answers to some of those unknown factors.
Wonderful. What stories, be they novels and television shows, whatever, what stories have inspired you to want to learn more about the universe?
Most of the stories I think that have really deeply inspired me are the real ones of our exploration of space so far, in terms of watching, as getting to watch as we saw the Voyagers go further and further out through the solar system and discover things that were new. I took a class as an undergraduate about what we were going to learn at the Neptune flyby by Voyager, based on what we knew so far. And when we had the Neptune flyby 6 months later, so many of the things we thought we were going to learn, we learned very different things. And so that those constant surprises, and the fact that the solar system and the beyond has a better imagination than we sometimes do, is one of the things that really inspires me to keep looking outward and looking beyond the next horizon.
Oh, fantastic. Yeah, there's so much serendipity in some of our exploration. From plumes out of Enceladus, the surface of Titan, all these discoveries and things. We always think we're going to find it one way, and then it's completely different. There's so much for us to learn. So another question: if you could go back in time and visit yourself at the very beginning of your career, what advice would you give yourself?
It's okay if it's not easy, right? It's often we look at people in careers and think that because they are, because of where they are, that it must have been easy for them to get there. It's not always easy, and that's okay. If something takes multiple times to get it, it's can be really worth putting the effort in to keep trying to get there. But just because something doesn't come easily the first time you try it doesn't mean you can't do it, and it doesn't mean that by persevering and pushing through that you won't be able to do it even better as you move ahead. So I think that would be the biggest thing, that it's not. Things don't always come easy, and that's okay. It's okay to keep trying when they don't.
That's wonderful. What is something that excites you, beyond Dragonfly, about the future?
I'm really excited about a lot of the upcoming exploration we're doing, and the next generation of explorers, and what people are going to think about next. We are so fortunate in our solar system, in terms of the variety of destinations and the complementarity of the destinations, right? The different things that we will be able to learn at Europa and Titan and Enceladus and the Uranian satellites, right? Each of these give us a different story, a different history, and a picture into the realm of possible scenarios for planetary histories, for the histories of worlds. And I just can't wait to learn about all of them, frankly.
I love that. One more question from me. What's an unbelievable science fact that still blows your mind?
The the discovery of oceans in so many of the icy satellites in the outer solar system is fascinating. The fact that there can be these oceans, and not just in one, but in many worlds, is that I still just find that incredible, and I can't wait till we get to explore them.
Absolutely. Thank you so much for that. We are going to open it now to our audience questions. So for those watching right now live in the YouTube chat, please ask your questions. If you are watching the recording later, of course, we can't answer those questions now, but I will try my best to get to them in the comments later. So let's go first off with a question from Jim Pass, who is at Astrosociology on Twitter. Jim wants to know how the Dragonfly mission to Titan is going to compare to the Ingenuity mission, which we, of course, have now seen, flying as a small drone on the surface of Mars.
Yeah, Ingenuity's been spectacular. It's so exciting to see flight on another world in our solar system. So there are a number of ways in which exploration at Titan is different from the exploration with Ingenuity at Mars. One is the scale. The Martian atmosphere is very thin, and Mars has higher gravity. It's a little larger than Titan. So at Titan, we have an atmosphere that's 4 times as dense as Earth's atmosphere, and that has 1/7, and Titan has 1/7 the gravity of Earth. So it's actually physically easier to fly on Titan. Like a person could put wings on and soar over the surface, which would be a really excellent future mission to Titan. So on Titan, the Dragonfly octocopter is about the size of the Perseverance rover, as opposed to the Ingenuity, which is has to be much smaller simply because of the dynamics of flight in the Martian atmosphere. On Titan, we can actually take something the size of Perseverance and fly from place to place, which allows us to take a very capable payload, the same way we've been exploring on Mars with the rovers. Another difference is that that we don't have a fleet of orbiters at Titan yet, sadly. And so Dragonfly has to do direct Earth communication from the surface of Titan. So all of the data will come directly from the surface of Titan, as opposed to being relayed through satellites, as we're able to do at Mars. But one of the areas that's similar is that even though Mars is much closer and the light time is much shorter, Ingenuity has to fly completely autonomously on the surface of Mars. And so we have that experience on Mars already, and Dragonfly will be also flying completely autonomously at Titan.
That's fantastic. And so you mentioned, all these orbiters we have at Mars where we can, send data links through orbiters back to Earth. And so we have to communicate directly, but we also have a lot more imaging. A question from @science_sponge on Twitter is there possibility of having cameras doing high definition images of Titan like we have for Mars? And I guess the question is, at what level, what resolution will images be taken from Dragonfly?
Right. So we have global mapping from Cassini at very different wavelengths. We have radar mapping at 2.2 centimeters down to near infrared imaging. On these, the resolutions of those are at the 100-meter scale. So we can use that global mapping. We know where we want to go. We know aspects of the surface to be able to plan Dragonfly. But we don't have HiRISE in orbit at Titan, and so Dragonfly will actually scout out its own sites in advance. And by virtue, because we're able to fly, we can actually use Dragonfly to do our own scouting. And so we'll fly out, take images of the surface, come back to our landing site, and then play those images back to Earth to decide where we want to go next. And we use Dragonfly to do its own scouting. We'll have images at resolutions ranging from meter scale down to very, very high resolution imaging of our sampling of the sampling site. Where we do drilling to break up the surface material to bring into the mass spectrometer, and there will be imaging at the scale of grains, so that we can really understand the details of the surface at the sampling site. So we'll have this whole range of kind of nested imaging at different scales.
Wonderful. Our next question from AC is about the surface temperature of Titan being just slightly warmer than liquid nitrogen. Would we expect the metabolism for life as we know it? And I think I'll start off there that, Dragonfly is not an astrobiology mission directly. It's not directly looking for signs of life because, yes, it is very cold on the surface of Titan, as you've mentioned. But as you mentioned as well, like we're exploring this realm where there has been an impact crater and there could be different energetic systems. What do you think is kind of the vision? What could we discover with Dragonfly in that realm?
Right. So as you say, Dragonfly is primarily a chemistry mission. We want to understand the chemical steps that occur before biology, and how far that chemistry can have progressed in this extraterrestrial environment in the outer solar system. Right. We can't easily study the chemistry that occurred before life here on Earth because we've got biology on top of it everywhere, and so that's really what we're looking for. We do, because we're making detailed measurements of aspects of Titan's, composition and chemistry. We do have the capability to identify a variety of chemical biosignatures if chemistry on Titan at some point in the past did take the leap to biology. 94 Kelvin certainly isn't conducive to life as we know it. But the Titan environment is very protected. There's an atmosphere that protects the surface from radiation, for example. And so if there are molecules that, were created very long ago, geologically speaking, they won't break down at the same kind of rate that we're used to on other targets. And so we'll be able to make those measurements to understand, we'll be able to measure that chemistry because it's an environment that will preserve those chemical products. But yeah, fundamentally, we're trying to understand the chemistry that occurred before biology.
Yeah, and that chemistry is really important. I recall when I was in graduate school, I took an environmental organic chemistry course, but the professor allowed me to do a project for the course focusing on Titan atmospheric chemistry that we knew of. And at that point, it was really, we did have measurements from Huygens, and we had some knowledge from Cassini, but a lot of it was basically modeling, trying to figure out based on known photochemistry and the ethane, methane precursors, nitrogen precursors, what is possible within the realm of energetics and the chemistry available. We have a question from Upgrade Me BB on YouTube. They want to know if we'll be using something like artificial intelligence to generate models to kind of simulate potential chemicals we might find with Dragonfly at the surface or the atmosphere.
We are doing work in terms of modeling and in fact generating, literally producing the kinds of molecules that we might find on the surface in the laboratory. We want to have kind of a library to be able to compare the measurements that we make at Titan II so that we can interpret that. So we can do that through modeling, but there's also, you can also generate a lot of these materials in small quantities in the laboratory. And one of our team members, Dr. Sarah Hurst at Johns Hopkins University, has a laboratory where she can build some of these carbon-rich tolins that we expect to be on the surface of Titan. So that'll be a fascinating comparison to see if what we build in the laboratory or what we model is what Titan is producing, or if once again Titan surprises us completely and has gone off and developed things in a different way than we predict.
Oh, fantastic. A question coming in from Valentin at Valu_66,000 on Twitter. They want to know if Dragonfly is going to actually study any of the lakes at the surface of Titan. Titan has these hydrocarbon lakes at the surface, and specifically, Valentin says they would love to see photos of these lakes up close.
That would be spectacular. So Titan's seas and most of the lakes are near the North Pole, are at very high northern latitudes, and the time scale for the New Frontier for our mission in the New Frontiers program is such that we arrive in by 2034. This is about one Titan year after the arrival of the Huygens probe. And so that's actually very fortuitous in that we actually have measurements of the atmosphere from Huygens, and we know what the weather was like in the Titan system from Cassini observations when Cassini arrived at Saturn and Titan. So that's excellent. But that time in Titan's year is northern winter. Titan has seasons like ours. The Saturnian system is tilted a little more than the tilt of the Earth-Moon system. And so it has seasons just like ours, except they're, several years instead of a few months long. And so when we arrive, it will be late northern winter, and the northern latitudes will still be in northern darkness. That means that not only is there not illumination for imaging, but because we are doing direct to Earth communication from the surface, if if the sun isn't up in the sky, the Earth isn't up in the sky, and so it wasn't possible in this time frame to explore the high northern latitudes simply because of the season. So we have chosen to go to a target of astrobiological interest where liquid water and carbon material may have been able to mix at the site of a equatorial or near equatorial impact crater for this mission. But unfortunately, we won't be able to get to the lakes and seas this time. Although I agree, it would be spectacular to get images of those shorelines.
It's a little saddening, but I imagine just like everything in our planetary exploration, we'll discover all new things with Dragonfly that will be remarkable and give us yet another reason to go back and explore some more. We have a question coming in from Rendering Reality 3D Animations on YouTube. They want to know if we can describe how Dragonfly will study atmospheric differences with altitude, specifically in like boundary layers in the atmosphere, changes over a diurnal cycle if there is one for us to explore during Dragonfly's mission while we're looking for the chemistry of the surface and atmosphere of Titan.
Yeah, so we want to be able to put the measurements we make of the detailed chemical composition of different materials on the surface of Titan into the context of the Titan environment to understand the environment itself and the habitability, how things vary from location to location. So we have the imaging, we have the geophysical measurements, and we have a suite of meteorological sensors to measure aspects of the atmosphere, pressure, temperature, wind speed, wind direction, etc. And we will be monitoring through the Titan day, monitoring the conditions through the Titan day. The Titan atmosphere actually doesn't change a lot with the dense atmosphere. It's quite sluggish, and so the surface temperature is day to night, winter to summer. It really only changes by about a Kelvin, but we'll certainly be measuring that to understand the atmosphere and its variability. We'll be able to do some measurements with low altitude. We don't need to fly terribly high in our mission operations plan to traverse from place to place across the surface. We'll probably only fly at an altitude of a few hundred meters, but we do have some measurements planned during the last stages of our initial descent through Titan's atmosphere, and we may be able to fly to do atmospheric profiles to slightly higher altitude, but not up to like the tropopause or something like that, just in the very lowest part of the atmosphere for this mission.
Very cool. And Titan has a very thick atmosphere. We did mention earlier this idea of sampling from the surface. Well, one of our users, AC on YouTube, wants to know if the RTG will be used for melting ice or what kind of drilling process we're using on Dragonfly to sample the surface.
Yeah, we have a rotary percussive drill So this breaks up the surface, and then we can actually use pneumatic transport because we've got this great atmosphere to just like a vacuum cleaner, you just suck the material right into the mass spectrometer. And the fact that the atmosphere is so cold allows us to keep those materials cold until we get them into the mass spectrometer to make measurements, which is very, very important as well. The MMRTG, the multi-mission radioisotope thermoelectric generator that we use for power, we use that to charge a battery. There's a lot of what's typically referred to as waste heat that comes off of the MMRTG. We use every bit of that to keep the interior of the lander warm. So the exterior of the lander will be basically the temperature of Titan. It will be equilibrated with the Titan environment, and we have a thick layer of insulation around the lander, so that we keep all of that heat inside to keep the the instruments functioning, et cetera. So there won't be any heating of the environment by Dragonfly in that sense.
Oh, fantastic. I love these conversations so much because they always like bring things to my mind, imagery of the, this rotorcraft lander. Now the outside is like so freezing cold, and it kind of just like brings this vision to my mind of the outside metal being freezing cold, but the inside having this loving heat from us giving it the RTG to heat it up inside. And that kind of is a fun way to jump into this next question, which I really appreciate, from Tasha on YouTube. Tasha wants to know, what is something about Titan that you would love to see represented more, or maybe represented better, in our artists' impressions of Titan?
I think the variety of different geological environments and just how familiar they are. Sometimes when we think of extraterrestrial worlds, we think of very alien environments. And I think one of the things that struck me about Titan is in some senses just how Earth-like it is and how familiar it is. I still remember the images that came back from the Huygens probe. The first time I saw one of those images from the descent imager showing the channeled landscape on Titan, and it was instantly so recognizable and so familiar. And here we are on this icy satellite out in the outer solar system with all of these different materials and very different conditions, and yet we're seeing something that you immediately know what it is when you look at. And so that kind of balance of familiarity and on this very different world is something that always strikes me, and I'd like be happy to see that kind of balance struck.
Yeah, I love that.
And a number of artists do a good job of that. Of course.
Wonderful. Well, maybe we have some artists watching right now who want to take on that task and create some cool impressions and visuals and graphics for us to see. One thing we've not really discussed is how Titan became such a methane and ethane-rich world, and what we know. User Arunava Padar, who is one of our past Young Scientist Program participants at Blue Marble Space Institute of Science. Arunava wants to know how Dragonfly might help us understanding the origin and history of the methane and ethane and chemical inventory of Titan.
Right. So one of the things we want to do is understand what the role of the equatorial regions are in the broader, hydrological cycle on Titan. There are a lot of outstanding questions about Titan's hydrology. Given the nature of the dune fields at Titan's equator, it seems like in general it must be an arid place. On the other hand, Cassini did observe some rainfall at some seasons at low latitudes, and so understanding that hydrology, whether there are near surface reservoirs of liquid is going to be very important to understand. The Huygens probe potentially detected, that the surface there may have been damp, and so that kind of measurement, the measurements that will allow us to get at just it's very shallow surface, but that kind of measurement is going to be important. We also have the mass spectrometer also has the capability to measure noble gases, some of the noble gases, and that on the, kind of stepping back to the big picture, will help us understand the nature of the atmosphere, and provide some information about the atmospheric history, which of course there's still outstanding, very fundamental questions about Titan's unique atmosphere.
Absolutely. And it is a very thick and dense atmosphere. It's 1.5 times the pressure at the surface than we have here at sea level. And it's a very thick atmosphere. I love pointing out for students that, like, the International Space Station, where it's orbiting the Earth, would very much still be in that very thick, hazy layer. Our user Miles Foley on YouTube wanted to know if we could see a Saturn rise photo from Dragonfly looking up. But again, it's a very thick atmosphere. And so maybe not. I'll let you answer that question. But what do you think we'll see if we look up with Dragonfly?
Right. So so Titan's atmosphere is thick. Our imaging with Dragonfly is at visible wavelengths, mostly visible, just into the near infrared. The visibility of the atmosphere in terms of the methane transmission spectrum is much better out into the infrared. But because we're down within the atmosphere, at the base of the atmosphere, we can see fine to explore the surface. Looking up, what we would see is the kind of orange sky. So we wouldn't be able to see Saturn in the sky for a couple reasons. One is because of the opacity of the atmosphere. When you're looking through the full optical depth of the atmosphere. But the other is that Titan is tidally locked to Saturn. So the same, just like our moon, the same side of Titan always faces Saturn, and we're landing on the opposite side from where Saturn is. So even if we were able to observe at a wavelength where you could see Saturn, it won't be up in the sky above Dragonfly. So we'll have to look for a future opportunity for that picture, which would be spectacular.
It would be pretty spectacular. Again, another reason we'll have to eventually go back again and do even more work. And now in my mind, I can't help but like visualize the Titanian atmosphere as like this orange haze above this beautiful frozen on the outside Dragonfly, if it chooses to look up. Again, that's part of the fun of these conversations, is just to think of what's going to happen, what's likely, what we would see ourselves, and maybe even to personify Dragonfly a little bit. We did note, our team, that in the current iteration of the design that we're at now, that it does look a little bit cuter. It's like it got like a little button nose on the front of it. Can you explain what that change was?
Oh, there've been a number of changes in the design as we've gone through our design iteration in the preliminary design phase, coming up to our review just the end of last month. A lot of this has been a lot of the design changes have been focused on. We want to make sure that we're as aerodynamic as possible. It's not, the most aerodynamic shape, but it's definitely more aerodynamic than it was, to be able to really, simplify flight, enable our flight, or better enable flight. We're also reducing, keeping our mass as low as possible. So a lot of the work we've done is to simplify aspects of the design, to reduce risk as much as possible as we can through design, and some of those things are showing up in the new design in terms of the streamlining and the simplification of the exterior as well.
I love that so much. We do have more questions, unfortunately, for our audience and for me. We're running out of time to have you on the show with us here. For the audience, there is a remarkable website for Dragonfly you can check out. Lots of really incredible mission information, a really wonderful gallery of images and such for understanding this mission a bit better. I hope you're as excited for it as I am. Dr. Zibi Turtle, thank you so much for joining us for Ask an Astrobiologist.
Thank you. It's been so fun to talk to you today about Dragonfly.
Yeah, it's such an incredible mission. I'm looking forward to it. For those of you watching, if you'd like to learn more about our upcoming episodes, you can always tune in on Twitter at NASA Astrobio. You can check me out at Cosmobiologist. We also have a sign up for the mailing list for the NASA Astrobiology program. Of course, we're also brought to you by SegaNet.org. You can find out more information about resources and upcoming articles about astrobiology there as well. So thank you all for tuning in and joining us and learning a bit more about Dr. Zibi Turtle and about the Dragonfly mission that's coming up on its way to Titan. So as always, remember, until next time, to stay curious.